Okay, so let us start. So the topic that is I am assigned for today is section 6 of Humphreys. Okay. Which is titled Complete Reducibility. Okay, so let me put down, lest I finish somewhere in the middle. There is very little chance of that happening, but nevertheless, because I think there is enough time. But nevertheless, I would just like to put down the statements of all the theorems right away, and the statements are it is possible to understand, appreciate the statements, apply them without really worrying about the proofs. Okay, we will worry a little bit about the proofs, but at least on a first pass, if you can just understand the statement clearly, know what it means and apply it, you will already, it's already something. Okay, so that should be a first goal. So there is this theorem which has been talked about now several times, but it's a very important theorem, and so I'll put it down on the board. So theorem, and this is due to while it was proved maybe sometime in the 1920s. Okay, although apparently the theorem was Cartan was using the theorem without proving it. So apparently this is what I've heard. So, but Weil finally gave a proof of the theorem. Okay. So G semi-simple, V finite dimensional, G modulo implies V semi-simple. It's a very simple statement. If you have a semi-simple, a finite dimensional module over a semi-simple Lie algebra is semi-simple. Okay, what it means is, so this is complete reducibility. This is the statement, and what does V semi-simple mean? It means V, so recall V semi-simple if and only if it is a direct sum of simples simple being simple or irreducible are the same thing, no non-zero invariant proper submodules, if and only if it is a sum of simples. Okay, so what this means is you can understand, hope to understand completely any representation if you just knew what all the irreducibles were and how to put them together, or given a representation, how to decompose it into irreducibles. Okay, so this is one theorem. The other theorem, again very important, that we are going to, I'll again put it down on the board. So I don't remember if this was covered in Upendra's lecture. So let me, before I put down the theorem on the board, let me recall for you what the Joran decomposition means for a semi-simple Lie algebra. Okay, so, okay. By the way, has Upendra proved that every inner derivation, every derivation is inner for a, no, okay. So here is a state, okay, first here is a, we'll do a theorem or proposition. So this is an important, it's worth calling it a theorem, okay. G semi-simple, I'll just shorten it to this, okay. Every derivation of G is inner. So what does this mean? So let us understand the statement. Okay. So there is, if you have any algebra, there is, you can talk about the derivations of that algebra. In this case, we can talk about the derivations of this given Lie algebra. Okay, semi-simple. Now, recall that there is the add map. The add from G goes to GLG, but actually it factors through the derivations. Right? The statement says that this map is onto if G is semi-simple. Okay? So this is onto if G is semi-simple. This of course you can write for any Lie algebra. The point is this is onto if G is semi-simple. Okay? Okay, so using this you can do the following. Now look at so Joran, let me define Joran decomposition. Okay, before let me just say a few words about this proof. You can use this either using Cartan's criterion or using the complete reducibility. There is a proof in the book. Humphreys uses Cartan's criterion. There is an exercise which says prove it using complete reducibility. Okay. In any case, we'll see whether we can do the proof in class or not. It can be deduced not completely trivially, but fairly easily given one of these theorems. Okay. But let's look at what this implies. So this gives us this notion of Joran decomposition. Let's understand that. Okay. Now, so G is semi-simple. X is in G. Right? Okay. Let's look at add X. Okay, if you look at add X, where does this live? This is in, you can think of it as a linear transformation on G. Right? Or in G. Now, therefore, this has, okay, we are always working, I didn't say that, but the underlying field is a field of complex numbers. Okay. So, all of that. We can talk about these as linear transformations on G. Okay, these are the semi-simple and nilpotent parts. So one of the exercises that we did last time was recall Joran decomposition. What it says is over an algebraically closed field, not to get too technical, if you have a linear finite dimensional vector space and a linear transformation on that, then there are elements S and N. If T is your linear transformation, there exists a unique decomposition such that T is equal to S plus N. S and N commute. S is semi-simple, meaning diagonalizable, and N is nilpotent. Okay, this is the statement. So you can take this and form its take its semi-simple part and its nilpotent part. Okay, these again belong here. Okay. Now, if you recall the exercise, another exercise I gave, and this is the semi-simple and nilpotent parts of a derivation are themselves derivations. So, not only, so this is a derivation, this not only belongs here, but actually belongs here. So, the semi-simple part is a derivation, the nilpotent part is a derivation. Okay. So, what we get is that since the semi-simple and nilpotent parts of a derivation are themselves derivations, what we conclude is that add x s and add x n belong to der G. Right? Okay. Now, you see this map is onto, however. See, so far I didn't use the semi-simplicity at all. You could have done this. So far so far we don't need this. Okay, but now I am going to use it. So this is semi-simple, means this is onto. Which means I can take this add xs and write it as, so there is a unique element here. Why is that unique? Because this is also injective. Okay, because G has no center. Okay, so this is so let me write it. G So there is a unique element, call it x sub s. Now that's notation. So there is an x sub s such that its add right, and there is an x sub n such that its add is okay, and these commute because, so let's compute. I want to show that these commute in the sense that now what does the word commute mean for elements in a Lie algebra? It means that their bracket is 0. Okay, so I have to show that their bracket is 0, but I can apply add because add is a one-to-one map. I can, to show this is 0, I can just apply add, but then add is a Lie algebra homomorphism. I can push it inside, and then I know I get these, and then that's 0. Okay, so now you can write your. So what we have is add x, therefore, is add x sub s plus add x sub n. Right? Yeah. So xs, to show that this is 0, since add is 1-1 map, I can apply add and then show it is 0. Okay. Now, so enough to show. So because, so I'll write because and this I know is true because these are semi-simple and nilpotent parts of a given linear transformation, which I know by choice commute. Okay, that's the proof. That's okay. Okay. Now, what was I saying? So I know that add x is equal to add xs, and but these have chosen now like this. So now add is 1 to 1, so I can write so I get unique elements xs and xn with the property that xs and xn commute, and the image of add xs, x is equal to xs plus xn, xs xn equal to 0, add xs is semi-simple, add xn is nilpotent. Okay, and that is called the Joran decomposition. So given, so let me write it, given, so what is, given x in G semi-simple, there exists xs and xn such that those properties. That's the, and it's unique. There exists unique pair of elements xs and xn such that these, I mean, why is it unique? If they were not unique, you would get a contradiction to the uniqueness of the usual Joran decomposition. Okay. Now, mind you, here the notion, this semi-simple is, I've used it quite strongly, as you can see, because we have used it here in saying it's 1 to, and also saying map is add is 1 to 1. Okay. The fact that add is 1 to 1 is not so serious. It's the lesser of the two. What is this ontoness is the one that's small. Okay. Now here is and as an application of complete reducibility, the following theorem is deduced in the book. Okay, it's called the preservation of Joran decomposition. It's a very important theorem. Okay, so if you, it means a lot. So what it says is the following. So take G semi-simple. Okay, before I say this, notice that I can talk about now in any semi-simple Lie algebra, I can talk about semi-simple and nilpotent elements. Namely, those I call an element semi-simple. These I call the semi-simple and nilpotent part of X, and an element is semi-simple if it is equal to its semi-simple part. An element is nilpotent if it's equal to its nilpotent part. Okay, so I can talk about semi-simple and nilpotent elements. The statement says, if you have a semi-simple or nilpotent element, then its image in any representation is semi-simple or nilpotent accordingly. Okay, that's the so V a finite dimensional G module. So semi-simple, respectively nilpotent elements of G have semi-simple, respectively nilpotent images in under the representation map. Okay. In particular, that means from this it's very easy to deduce that the Joran decomposition is preserved. That is, you take so in particular, so I'll say if x equal to xs plus xn is the Joran decomposition in G, and phi, suppose we represent the map, the representation map by phi, then is the Joran decomposition in GLV of phi x. That's the statement. Okay, it's a beautiful statement. So, if for example, if I take SL2, I know H, the element H, how it acts. It is a semi-simple element, because for the adjoint action, x, y and h are eigenvectors with eigenvalues 2, 0 and minus 2. So, it is a semi-simple element, which means its image in any finite dimensional, the finite dimensionality is important. It cannot be, that hypothesis cannot be removed. Okay. So, in any finite dimensional, in any case we are interested mostly in finite dimensional representations only. We will have occasion to, just for a fleeting minute or two, worry about infinite dimensional representations only insofar as they are related to finite dimensional representations. Okay, so if you have a finite dimensional representation, the image of H in that endomorphism of that vector space is semi-simple. So, you can decompose your vector space into eigenspaces for H. Okay. More generally, if you have, for example, SLN, and then look at the diagonal matrices in SLN. Okay. Now, I claim the diagonal matrices are semi-simple. Why is that so? Well, they are semi-simple for the standard action by definition, but then one of the exercises said if something is semi-simple for the standard action, then add of that is semi-simple. Right? One of the things you had an exercise was, okay. So, add is semi-simple if you want, and therefore it's semi-simple. So, you can take a module for SLN, decompose it into eigenspaces, common eigenspaces for all elements of all diagonal elements. Okay, and that is a very basic thing and very basic way to understand the structure theory of the structure of representations of a semi-simple Lie algebra. Okay. So, that finishes, I think, the set of theorems that's the statement of the theorems that we will do today. Let me introduce the very important, again, technique, one possible technique to understand complete reducibility and its and these corollaries. Okay. So, that's the notion of the Casimir element. Okay. It's one of those things, curious things in a formal setup. A thing like this, a Casimir element, it does not have very important place. So, you see in Humphrey's book, it's hidden somewhere, and it just makes a small appearance and then goes away to the background. But somehow I think it is, you know, if you, it lies very at the very heart of the matter. Okay, so although formally it is, it looks like you are doing something very special, something very, you know, you are writing something particular. It's not very, it feels like that, but actually, at least in the beginning. But this is a very important element, and if the more you understand it, the better, the more deeper your understanding. So, okay, so let me start with an example. Okay, so so for SL2, so in USL2, we know what this means, right? SL2 is the Lie algebra, 2 by 2 traceless matrices. U means the universal enveloping algebra of that. Okay. Now, one of the exercises tutorial sheets took, you know, sort of wrote this element down and claimed that it was in the center of the universal enveloping algebra and asked you to check it. Okay. Now, this is an example of a Casimir element. Okay. So, this is, I hope you did it, but if not, you should do it. Just check that it is in the center of the universal enveloping algebra. That brings me to, before I start talking about more about the Casimir element, I should recall or Schur's lemma. So, Schur's lemma is a general statement about when a module is irreducible, right? So, what it says in this in our context is, if V is irreducible for a Lie algebra G, so over base field, let's assume complex numbers, then, so let me write like this, end G C B. What does this mean? The maps from V to V which are G module morphisms. Okay, what should this be? Right, there are the only G module homomorphisms from V to V are nothing but multiplication by a scalar. This is the statement. Okay. Now, okay. Now here you have an element in the universal enveloping algebra, which means it commutes with all elements in the, in particular in the Lie algebra. Okay, which means it will represent, if you look at its image in the endomorphism ring, endomorphism algebra of any representation, it will be a G module homomorphism. And therefore, if this is irreducible, it will represent a scalar. And somehow this, the analysis of this scalar, what its value might be, underlies the application of this Casimir element. Okay? Okay, let me also say a few words here about, a few words here about UG. So what is the, so we learnt, can you recall for me the universal property of UG? If you have, it is universal for Lie algebra homomorphisms from the given Lie algebra to any associative algebra, right? It's an initial element in that category. So if you have from G to any associative algebra A, then this is a given, the canonical one. There always, this always factors through this, such that this diagram commutes. Okay. So as a, in particular, I could replace this A with okay, that's what a representation is. If I take a representation of G, what does it mean? It means I wrote specifically end V rather than GLV because I'm thinking now of it as an associative algebra rather than a Lie algebra. You could write GLV, there is no. So G to end V, there is a Lie algebra map, right? So that is a representation. But this is an associative algebra, which means there is a unique map from UG to NV, which means this is an associative algebra map. So which is exactly the same thing as saying V is a UG module. To say that if you have a module for a ring, what does it mean? Or module for, if you are working over integers, then you would say you take an abelian group, take the endomorphisms of that abelian group, that's a ring, you have a morphism from your ring to that ring. Okay? But here instead of Z we have a base field. So what the correct change is, you have an underlying vector space and you take the endomorphisms of that vector space, that gives you an algebra, and you have a map from your given algebra, associative algebra, into that, a map of associative algebras. Okay? So this is precisely the statement that that there is a map like this is saying that V is a module for UG. Okay? Now, therefore, this what I have just talked you through is the solution to an exercise in Anupam's tutorial sheet, which says that G modules are nothing but UG modules. Okay? So once you have a G module, it is naturally a UG module. And if you have a UG module, surely there is a G module by just taking the composition. Okay? So, and I mean, this seems like very obvious, but the point is, see, you've gone from one theory to another. What you've said is that modules for Lie algebras are really nothing more than modules for universal unlimiting algebra, and therefore you can bring to bear on the theory of Lie algebras all that you know about modules for associative algebras or rings. Okay? This is a very strong, so you can pass from one to the other. Okay? So it is the analog of the group ring. If you have a finite group, then you know that modules for the representations for the group are nothing but modules for the group ring. Okay? So this is the UG is the analog of the group ring. Okay? Take an irreducible representation, then it is necessarily acts like a scalar, and then we have to worry about how, find out what value that scalar is, etc. That will give you tremendous insight into the structure of those the representations. Okay? Okay, so let me try to define the Casimir element, but I will do it. I didn't particularly like the way Humphreys did it, but I shouldn't complain too strongly because he's writing a textbook. He doesn't have the advantage of standing in front of his audience. Okay, so it's a little non-canonical. It's what I'll do is a little more abstract, so perhaps you will like it less, but to me, unless I did it this way, I wouldn't understand it. Okay? So I will do it my way, and it's slightly different from Humphreys. He's being very concrete. I'm being a little more abstract. But when I write things down, you don't have to check any uniqueness. It's always unique, and things work out, provided you accept certain statements that I'll make, which will sound very natural, but you'll have to check them. Then it's much easier for me to understand. So I'll do it that way. So let's recall the following. So I'll write a big, so this board will contain a big commutative, some kind of diagram, in which I'll put down things, and I'm trying to define the Casimir element. Okay, so I need some preliminaries. This is what I'm doing now. Okay, so in the tutorial on tensor products, a very basic isomorphism was mentioned, namely, let me write it here. So Hom VW as a vector space is equal to V star tensor W, right, for V finite dimensional. Maybe it was assumed V and W are finite dimensional. It's enough that V is finite dimensional, but it's important that otherwise this is not true. But we are in, not to worry, we are in the finite dimensional situation. Okay. So in particular, I can write end V is equal to V star tensor V. Okay. This is a standard isomorphism, and the point is it's not just as vector spaces. If you are thinking of G modules where G is a group or a Lie algebra or I do not know of any situation where this would not be, the isomorphism would not hold also in that category. Okay, I want to start with end of G, where G is a Lie algebra, just a Lie algebra. I am not assuming semi-simple for the time being. Okay, so applying this, what would I get? All right, and then provided, so if there exists a non-degenerate form, let me assume that the form to be symmetric. You can actually just work with non-degenerate itself, but then it's a problem of right, left, etc. But let me assume that the form is non-degenerate. There exists a non-degenerate symmetric bilinear form. So again, this was done in the tutorial on tensor products. If you have a non-degenerate, an isomorphism from V to V star is nothing more, nothing less than having a non-degenerate bilinear form. Okay. So if I have a non-degenerate bilinear form, I can identify G star with G. So G is finite dimensional, and let's say over complex numbers. Okay. So then G sits inside UG, right? So I can write this is inclusion. So inclusion tensor inclusion, right? And then I have a map to UG. This is the multiplication in UG.
That is just inclusion as a vector space.
Or as a Lie algebra. Or as a Lie algebra. Yeah. Yeah, that's just inclusion as a vector space or a Lie algebra, right?
So the resulting map isn't necessarily an inclusion. Okay?
The resulting.
So the resulting map on the tensor product isn't necessarily an inclusion, is it?
Is not, is that?
Is it an inclusion as well?
Yeah, it is an inclusion as well. Yeah, it is an inclusion as well. Because all the tensor products are over vectors or over fields. Or over fields, yeah. Otherwise, you would be in trouble, but all the tensor products that you see here are over fields, so we don't have to worry about the non-exactness on the left of the tensor product. Okay, so if I had this, which I do in many cases, for example, if G is semi-simple and I have the killing form, I have a thing like this, and I have a very natural element here. Identity, I can take its image here, right? So I could take the identity here and its image there. So here take identity, and so take its image here all the way here, call it C, and that will be the Casimir. Okay. So there. Now let's do this. Let's do a little bit of a bit of calculation before we check that this is indeed a Casimir. Okay. So what is the choice involved? The choice involved is this form. Right? The choice involved is this form. If I change the form, I might get a different Casimir. Yeah, at least a priori. So depends. So this Casimir is of the form that I've chosen. Okay, one observation. So let's look at here. Here, if I have the identity and I choose so you've studied in the first tutorial that if I have a basis here, then of course we know the dual basis for V star, and if there is a basis for this and there is a basis for this, EI were the basis for this, Fj were the basis for EI tensor Fj would be a basis for this, right? So I'm asking you, suppose I choose a basis for V, then the dual basis for V star. How would you write the identity element this side? It's a natural question, right? And the answer is always, if I take E, I'll write it like this in physics notation. I suppress the summation. That's the and this is, so the point is the element E super I tensor E sub I summed over I, of course, which is suppressed, is independent. I can change the basis, but that element does not change. It's always the identity. Okay. So if you want to work this out, I mean, it's a simple calculation. So identity always maps to this for any choice of a basis of V. Okay. So if we do that, so here we have a form. Therefore, I have to choose a dual. So if xi is a basis for G, xi dual basis with respect to the form. So let's denote this form like this, which means what? I have x sub j, x sub I is delta ij. That's what it means. Okay. Then what would this element be? Well, this would go to identity, would go to a simple calculation. I'll write it directly here. It will go to this. That would be a representation of this. Then here and here would give me, if I suppress the I again, I mean suppress the summation, so this Casimir would be
dual basis in G itself.
In G itself with respect to the form, which means it is the dual basis in G star pulled back by the identity of, by identification through the form. Yes, and whenever there is an upper and a lower index, it's assumed that there is a summation. That's what I said by saying physics notation. Okay. So this is the Casimir. Okay. Now let's see that this is the Casimir. Okay. What is the form? The form, okay, so you have seen the you've seen the killing form, but I'll tell you something that is a little simpler, and which turns out in this case to be it's a multiple of the killing form, namely the following. So recall, trace, so xy is equal to trace xy. Is a non-degenerate form, non-degenerate symmetric bilinear form on end V. V finite dimension. Okay. So if I have a form on a vector space, and so if I have let us observe that if I have a form on W and V to W is a map, I can pull back the form from W to V. Meaning if you have a linear map, you can pull back. What does this mean? Let's just see how you can do this. What does a form mean? It's a map from W, tensor W, to the underlying field, which we are denoting C in our case. Now, if there is a linear map, you could take the phi tensor phi here. That would be a linear map from V tensor V to W tensor W, and therefore you would get a form on V. So you can pull back forms from when you have a map of vector spaces. Okay. So what I can do is, G is equal to SL2. Okay. There is it is sitting inside end of V, two-dimensional. And look at what this form is. This is a form here. So restrict the trace form to on just sitting inside because it's traceless. If I wrote GL2, what do you get? So let's compute. What is X? What is Y? What are X, Y, and H? Of course, these I don't have to worry about add. I just write what they are. This is just this. This is, and this is this. Okay. So what is the form? So if I write XHY, XHY, and compute the form here, what do I have to do? I have to take trace of x square. X square is 0. The trace is 0. XH. I'll let you do it. See, this is upper triangular. I mean, not strictly, but this is, and this is strictly upper triangular. So it's going to have zeros on the diagonal. Okay, so you can do it that way. What about XY? 1. So write out that Casimir. So I have to choose a basis. Suppose my basis is XHY. What is the dual basis? If I choose XHY as my basis, dual basis would be Y, H, H by 2, X, and then multiply and write. And that is that element. Okay. Now let me make some comments which will make it yes. Yeah, because X with Y is 1. So I have to, what does the dual mean? The dual means the element which is 0 on H and Y and 1 on X. Y is 1 on X and 0 on H and 0 on Y. Therefore, Y is the dual of X with respect to this form. Okay. and therefore this gives Casimir is xy plus yx plus h square over 2. Okay, now I'll make a few comments. So here we chose, see, this definition was made with respect to any symmetric. I assumed symmetric. If you don't assume symmetric, then you'll have to worry about left, right, etc. You can just do with this, but that may not be so pleasant. Okay, let's assume non-degenerate symmetric, and then you have this element. But the forms that we really like the Killing form, are not just they have some particular property, namely they are associative or invariant. Okay, by the way, the word invariant is used, Humphreys uses associative, but the word invariant is also used in the literature, perhaps more commonly used. Okay, so keep in mind, so the word invariant form is used, and it means just associative form. Okay, so the Killing form is invariant. Associative means the following. It just means that the associative law holds in the following sense. The reason why this is called associative is this. Okay. By the way, that just reminds me of an exercise. Why this doesn't make any sense, does it? I mean, when you stare at it, why should one worry about this? Right? It looks a very strange condition to put on a form. I mean, doesn't it? Or is it natural? If it's natural, then no problem. If it's not, then I'll tell you why it is natural. I can tell you why it is natural. Because it is the differential condition of a natural condition. Shiva, even you will agree that this is not natural. Although it's a differential condition. So let me make, this is an aside. So this condition, so this is associative or invariant. The form to be invariant or associative. The reason is, see, when you have a group, when do you say a form is invariant? When you have, so let's work this out, why this is natural. So when you have a group, a form is invariant if you have right? Now put, or VW, let me write, because let's not get confused between. Now put G is equal to 1 plus epsilon x and work this out. Okay? If you do this, then you will see, let's see if I do this, let's do this. What do I get? V plus epsilon xv, comma, W plus epsilon xw. Okay? That's equal to VW plus epsilon xvw plus Vxw plus higher order terms which I ignore, plus higher order. Okay, so cancelling VW, the natural condition of invariance for a Lie algebra would be this. If you have a form on a G module, it would be natural if this condition held. Well, apply it to the adjoint representation and use that it is antisymmetric, you would get this form. That's why it's called invariant. Okay? Okay, now let me make another important statement here. if I chose this form to be invariant, see, invariant means what? It is invariant under the group. See, you should think that there is a group acting all over, and there is something being invariant for the group. Sometimes you see the group, sometimes you don't see the group, sometimes nobody has seen the group yet, okay, as in the Kac-Moody case. But never mind, you should think that there is a group underlying, I mean, at least for feeling for, there is a group underlying everything, and the invariance means that thing is being, see, this was an invariant element for the adjoint action, right? So that's what is carrying through. If this is invariant, the whole thing is invariant, what do you expect to get here? You expect to get an element in the center of the universal enveloping algebra. So the statement I want to make, and I leave that as an exercise to check, is that if this form is invariant, then the corresponding element here lives in the center of the universal enveloping algebra. So statement is, if the form is invariant, should I stop maybe? Okay. If the form is invariant, then Casimir is in the center. Okay, so the proof exercise. Okay, that's a very natural statement. Okay, now let's see how I okay, so now let G be, so I've made essentially two sort of, so make this one, this is, that you can do this and you will get the Casimir here. The second statement is that if the form is invariant, then the Casimir belongs to the center. Now I will go on and assume G is semi-simple. Okay. Or before that, maybe I'll just put these together and make a comment. Now, what you can do is, if let G to end V or GLV be a representation, if the trace form pulled back to G is non-degenerate, assume this, then using that form you will get a Casimir, and that Casimir is called the Casimir associated to V. Okay. We get the corresponding Casimir is denoted CV. Okay, it belongs to the universal enveloping algebra of G. It was, remember, it was cooked up by using a certain representation. such that the trace form pulled back is non-degenerate to G. But it is in the center. So on any irreducible representation, perhaps V if V is irreducible, but any other whatsoever, it acts as a scalar if that representation is irreducible. Okay. Okay. Now let's come to the third point. So assume G is semi-simple. Okay, and V is faithful. In particular, that must be faithful. Correct. In particular, that must be faithful. But even if it is faithful, the trace form may not be. Yeah. So suppose G is semi-simple and V is faithful. So as Shiva points out, the faithfulness of the representation is necessary. See, I'm trying to. So we have made certain observations. So what we are saying is, if you have so what are we trying to do? We are trying to understand what a Casimir element means. It is a set of elements. Casimirs are some elements in the center of the universal enveloping algebra. Okay, their actions on representations hold. I mean, if you understand their actions on representations, then you understand a lot about the representations. That's the motivation for studying them. Okay, now how do we get them? There is a form underlying this, then you can define a Casimir. And what we have observed is that that form is invariant, then that element belongs to this universe. So I have to cook up invariant forms. How do I cook up invariant forms? The answer is, if I have a faithful, take a trace form on a representation, pull it back and see if it is invariant. I mean, see if it is non-degenerate. It will always be invariant. The reason why I do it this way is that invariance is guaranteed. Okay? So the only problem is non-degeneracy. So if it's non-degenerate, lo and behold, you have a form and a corresponding Casimir. Okay? Now, the next statement I want to make is, if G is semi-simple, then any faithful representation is the trace form restricted to G is non-degenerate. So the upshot is, given semi-simple Lie algebra and a faithful representation, I get a Casimir. Okay, that's the upshot. Okay. So here is what I want to say: G semi-simple and V faithful. Then the trace form pulled back to G is non-degenerate. So for that comes from, see, this is a very important statement, and as many important statements do, it relies on Cartan's criterion. Okay, so I'll just indicate how it comes from Cartan's criterion. So if you recall, so G I can think of as sitting inside GLV, right? So this is proof of this statement, why it is non-degenerate. G is contained in GLV, right? Now, one of the statements of Cartan says, if trace of X then G is solvable. I might have just stated it differently, but it is equivalent to what I have written. Okay, this is a statement. Now, now look back here. If the trace form is So now this is by Cartan. So this is recall. This is Cartan. Now this comes as follows. So if R is the radical, what does that mean? Trace of, so if R is the radical of this form, I want to show it's non-degenerate. I want to prove R is 0. What does that mean? Trace of x, y equal to 0 for all x in R and y in G. Okay. In particular, it is true for x, y, z in R. Therefore, R is solvable. So, in particular, okay, and it's invariant, therefore R is an ideal. So invariance of the form R is an ideal because the form is invariant. Just make sure that what I've written is I'm not push some detail under the carpet. It's okay what I've written? Okay, you agree. So you get yourself a solvable ideal. But that is 0 because you are in a semi-simple algebra, Lie algebra. Okay? QED, so R is 0. See, if you pull back the trace form is invariant. That's one of the nice things about a trace form. See, trace of x, y, z.
I'm sorry.
Yeah, sorry.
Why is trace x, y 0 when x is not?
That's from the definition of radical. What does it mean to say something is in the radical? It kills the form. It is 0. What is the radical? It is all elements x such that x comma anything is 0. Okay? Yeah, okay. Thanks. Yeah. And the radical of the Cartan's criteria says the radical of the killing form is the radical. In the no, is that maybe I overstated it? Ah, okay. Yeah, sorry. So sorry. Okay, yesterday we had this problem again. Yeah. So yeah, I take. Sorry, erase what I said. Okay. So finally, I want to make the following. See, what are we interested in finally? We are interested in representations of semi-simple Lie algebras. So I want to take a semi-simple Lie algebra and a representation, and I want to understand it. So I've said that Casimirs are somehow a tool to understand, and I want to produce Casimirs. and here I have assumed that it is faithful. Now I just want to make a comment saying that you can cook up a Casimir anyway, and you call that the Casimir of the representation even if V is not faithful. So I'll make a comment. Okay? So if G is semi-simple, so assume G semi-simple, V any representation. Okay? Then what do you have? G maps on to G prime is contained in GLV. You can always write it like this. Right? And you have G prime is now semi-simple because quotients of semi-simples are semi-simple, and you have a faithful representation. So you can get a Casimir for G prime. Finally, the Casimir is an element of the universal enveloping algebra, but in particular of the, so you can look at it as an operator on the endomorphism, that is operator on V. Okay? That operator you call the Casimir of G and V. Okay? So we say set CV, now this is in end V. By definition, this is of C with respect to G prime and V.
I know, but so in that identification between G star and G,
See, there is a form. I used a form.
right,
So that form, the question is, how do I get that form? I pull it back from the trace form on some representation. That's how the representation enters into the calculation. Yes?
So it's always associating on the D algebra itself, right? Always invariant.
Which one?
The form that you get.
The trace form, the trace pulled back of the trace form is invariant.
So that means that when you think of G as a representation of itself, it's an invariant form. Finally, it's a form on G, whichever way you get it. So if G is an irreducible representation, the adjoint representation is irreducible, then won't the form be unique up to scalars?
That's correct. So,
So for a semi-simple G, yes, because it could be one of the simple ideas. If you have
Aha.
a simple algebra, that seems to mean that the Casimir is unique. Is that right? Up to scale. For a simple D algebra.
that's correct. That's correct.
But if you have summands, then it could be coming from one of them or a linear combination.
Correct. Absolutely. So, correct. Okay. So so maybe that's what you were asking. So I.
so G semi-simple, if you use that killing form there, then this Casimir element is, uniquely defined. So what I mean says,
Yeah, it is defined. Yes, you could use the killing form, and then you will get the Casimir. If G is semi-simple.
yeah, and you're saying that for an arbitrary semi-simple module V, you will pull back the killing form to, when you say, then the trace form means the killing form.
It will be a multiple of the killing form. If it will be a multiple of the killing form, as Upendra points out, if G is simple.
Oh, not otherwise?
Not otherwise. See, the problem is you could take
When you say then the trace form,
the trace form on GLV. Okay, maybe we'll do some calculations. So maybe I've misunderstood some questions. My understanding itself is not very perfect. So yeah.
Always Casimir element will be unique. So it is the image of identity. So it is.
Yes. It is unique. Once we fix the form. Correct.
If it comes from the representation, you are viewing
You are also you
Just you are taking the
image of that. Yes, yes. Okay. Yeah. So if G is simple, that's correct. Yes. Yeah. Anyway, so maybe you should go on. I mean, because we. Padma, you had a question? Never mind. Never mind. We can go on and yeah.
What are you saying in this last point? Getting different forms will get different. Could you repeat what you said?
All I'm saying is, if V is any representation, not necessarily faithful, I construct the Casimir for G prime, and that is an element of, think of it as an element of end V, and call it the Casimir for V. It's only a, yeah, that's why I said in end V. Okay, okay. So one more calculation here. Okay, so let's calculate. So suppose V is irreducible. So I'll assume then what do I know? I have this element CV. So a calculation. It acts like a scalar, right? CV belongs to the universal enveloping algebra, center of the universal enveloping algebra. Therefore, it acts as a scalar on any irreducible representation by Schur's lemma. Okay? CV acts as a scalar on V. Okay? Now, suppose I compute the trace of this. So, let's call it C. Right? So, what is trace of CV on the one hand? It is C times the dimension of V. Okay? And on the other, it is trace of sigma xi. Okay, I'll write a summation because this time it is going to be important. So trace of xi, but this was dual form. So this is 1. And how many summations are there? Equal to the dimension of G. So I'm assuming it's faithful. So what I get is the action of this Casimir, the scalar C is equal to dimension of G by dimension of V. This is an important thing that underlies many of the proofs. Okay, so if you take an irreducible representation and look at how the corresponding Casimir acts, it acts as dim G by the dimension of the Lie algebra divided by the dimension of the representation space. On V. That's why I write C sub V. That's why those two traces are equal. Yes. So this is C sub V, and call this C sub V if you want. That's the scalar by which the capital C sub V acts. Okay. Now let me illustrate the use of this by proving a particular case of the of Weil's theorem. How this enters into the, how the Casimir enters into the proof of Weil's theorem, complete reducibility theorem. So let's do that. So we'll assume the following. So, so what you have to show is that any representation is a direct sum of semi-simples. Okay, but let's assume no loss of generality in assuming V is faithful. Okay, so let's assume that. And the important case is the following. This is how it is reduced. So this is codimension 1. Irreducible. So assume V faithful. And you have a trivial representation as quotient. So this is the, I'm following the proof in Humphreys. There are 3 paragraphs to the proof. The first paragraph is a reduction. The third paragraph is a reduction. The second paragraph is the crux. So this is the second paragraph. Okay. So so you have to show, so given, need to show it splits. Okay, so this is what we have to do. Meaning, it, of course, this is to prove the full theorem. This is only a special case, but you've reduced to this special case. It's enough. The rest of that I'm not doing. It's just an algebraic reduction. Okay. So how do we do this?
If there is a codimension 1 reduced.
So you are reduced to that case somehow. You know, somehow you're reduced to that case. Okay. So what I do is the following. Look at C sub V.
So therefore, I mean, any G module structure on, I mean, this G module thing on W lifts to V is what you say. Splitting. Splitting as G modules.
Splitting as G modules. As G modules. I mean, of course, not every splits in several ways as a vector space, but there exists a G module splitting. That's the claim. Okay. So look at CV. See, now the point is it belongs to the center of the universal enveloping algebra. So the main idea here is, if you have an operator that commutes with all the operators in the Lie algebra, coming from the Lie algebra, then its generalized eigenspaces are invariant for the Lie algebra. That's the point. Okay. So look at CV. First of all, so note CVW why? Because CV is defined as products of elements in the Lie algebra. If each one of them preserves the submodule, so does C. Okay. Now, the action, so let's write, so this is a certain element in the universal enveloping algebra. Let us look at its matrix for V. So suppose I try to write the matrix for V on V for this element, and I choose, so here is an attempt at writing the matrix of CV, where I write, this is the W part and this is the extra part. Okay. Now, what happens on W? W is irreducible, and CV belongs to the center. Therefore, it acts like a scalar. Okay. So, what I see here is that scalar I cannot write as CW because this is a CV. Okay. So, I just, but it is some scalar, so let me call it C. That I know. How does it act on the trivial module? On the quotient, which is the trivial module, every Lie algebra element acts as 0. This is a product, sum of products of Lie algebra elements. Therefore, it acts as 0. So, there is a 0. The thing is, it could be like this. Right? But the point is, there is a 0 eigenvalue. So, look at, there is a 0, 0 is an eigenvalue for CV. Therefore, there must be a eigenvector. Okay. Because this is 0. So, the matrix looks because this is a trivial module. This is a trivial module, so this is, okay. So, 0 is an eigenvalue for CV. Okay, so look at okay, the claim is that, say, the eigenvalue on W is non-zero. Now, let us see why. I somehow thought that would come from this calculation, but should I use a CW maybe? Maybe I should use a CW. Okay. Now, this is CW. This CW is dimension of G by dimension of W. Okay. So, look at the 0 eigenspace. So, what I conclude is this is done. So, what we wanted was something that is invariant, complementary to W, and complementary and a complement to W. So, the answer is that the 0 eigenspace does the job of this CW. Okay. So, I will stop here. Unfortunately, I couldn't get to the proofs of the preservation of Jordan decomposition, etc. But but I'm not unhappy about it, because those proofs are rather formal, and once you get used to some of these formal proofs, those are much easier. What we did today is much more, I think, it's a little bit harder to get out of the book. So I'm quite happy that those formal proofs, I'm confident you can, it's much easier for you to learn than from the book than this stuff perhaps. Okay, so we'll have tutorials at starting at 2.